Thanks for joining. Today I'll go and complete these two topics. We'll discuss about TCP and UDP, and then we have one hands-on lab related to understand, configure and verify IPv4 addressing and subnetting. So we'll do that one by one. TCP and UDP, these are two protocols. They are at the transport layer. So to understand TCP and UDP, we should understand different type of stack that we have. We have TCP IP stack and we have OSI 7-layer stack. Here you can see TCP IP, you have total 4 layers. It will start with, not like this, but it will start with physical layer, and then I have actually chart here so you'll understand. TCP IP, it will start with physical layer. So the name is network access, internet transport and application. It's like that. Actually, the actual model is this OSI model where we are telling that physical, data link, network, transport, session, presentation and application. All people seems to need data processing, like so many things, so many rhymes are there just to understand this, but better you'll understand, like everything start with physical where you are connecting the cables, then you have data link layer basically the devices has the burnt in addresses, then you have network layer where you are putting the IPv4 IPv6 addresses, then you have the transport layer where you have the TCP and UDP. So this is the topic. This is the topic that we have to understand. If you see the agenda, that in our agenda, understand TCP and UDP, compare their services. Where it is in the stack? In the stack, they are at the transport layer. If we are starting from physical, data link, network, after network, you should have transport. This is correct. Physical, network layer, physical data layer, then network, then transport, presentation, application. Little bit inconsistency, but here it is correct. Physical data link, network, transport, session, presentation and application. Session, presentation and applications, actually application layer is where your application lives. So for example, when you're doing the web browsing, you are using some HTTPS sessions or HTTP session. So those are falling under application layer. Any application like HTTP, HTTPS, you can see FTP, even I think Telnet. Yeah, Telnet is also one application using port number 23. So any applications that you are using, they are falling under application layer, right? We should understand at least the logic behind this OSI layer build, but practically we are using TCP IP model. In our labs and the devices, they are using TCP IP model. This is, you can think as a theoretical model. Still few devices are using OSI model, but in our devices, in all the networking devices, we have TCP IP stack, TCP IP layer, right? So clearly you'll see that network access where you're connecting the cables, this is your physical layer. Then where you have the MAC addresses, where you have at the data link layer. Then where you're assigning the IP addresses, logical address and routing addresses, those are at the network layer. In TCP IP stack, that is the internet layer. Then where you have end-to-end connection, error handling and all those features, that is TCP UDP, that is in the transport layer. Then where you are managing the session layer. Where you are doing some encryption, compression, algorithms, presentation layer. And finally, where you have the application lives, that is the application layer, layer 7. Okay. But in this layer, what we have to learn? In this stack, we have to understand about TCP and UDP. Now, it's very interesting actually. If you go deep inside this layer, it is actually very interesting that how things are glued together, how things are connected together. So what I'm telling, that suppose you have one router here, and suppose you have one switch, And suppose we have one workstation. This is the workstation. Suppose this is the workstation connected with the switch. So workstation to switch, switch to router, router to router, router to switch, and then switch to workstation. This is a workstation. Suppose this is switch. Suppose this is a router. This is, oh sorry, this is switch. This is where you have the destination, right? And this is your source. Suppose this is my SRC source, and that's my destination, source to destination. Now suppose you have to go there and utilize the services HTTP. You are doing web browser here. This is your server, and you are using HTTP S services, for example. Some web browsing you want to do. Now, when you will send your packet, it will go to the gateway. Routers will give you the routes to reach to the next hop. From there, you will go to the gateway, and then you will reach to this particular device. But since what type of application you are using application that is at the application layer, right? That means that that particular application you can access via port number 443, because HTTPS, they have port number 443. So interestingly, that see, when you are reaching to switch, what switch will do? What switch they are doing? Switch, they are learning the MAC address. So the local communication that is happening, that will happen via the MAC address. But once you reach to the router, how you will reach to the router and the gateway? Via some IP address. And how routers, they will build their routing table with help of IP addresses, right? So that means that your global communication will happen via IP address, and IP address significance that they will have the logical addressing, routing, right? What's the significance of the local address? That you have the physical address, MAC address, they are the burnt in addresses. So to reach to your gateway, you will use the IP addresses. Obviously, to reach to your switch, you are using MAC address. To reach to your router, you are using IP address. Router to router, you are using IP address. Again, in the reverse direction, when you have to go and reach to the, so this packet, the source packet, will reach to this switch and this particular destination, right? So first of all, it will come to this particular switch, right? In this particular switch, it will reach to the destination network, and then it will reach to this particular host, right? The host, destination host. But point here is this: when you have to go and use the services, then the transport will come into the picture, and transport will give you, either you are using TCP or UDP based application. Actually, there they have some protocol number. Suppose this has protocol number 6, UDP having protocol number 17. But to access the services, you need some sort of port reachability, and here they will, first of all, protocol will get mapped to the port number. So the transport layer will actually give you the port number mapping to the application layer. That's the story that is happening. That's the significance you have. So you will get the session TCP, and then TCP. Who will provide you this TCP communication? The transport layer. And then you will get the port number. So with port number only, you can access the services, because what you want to access the URL. you want to access some applications. Now those applications that we have, suppose these applications, the HTTP, FTP, how the lower level will come to know. So the HTTP, it is in the 7th floor and your network access is in the first floor. For example, your physical layer is in first floor, right? So first floor will not know what is happening in 7th floor. First floor will know only what is happening in the 2nd floor. So these two layers can communicate, right? Likewise, layer 2 can communicate to layer 3, right? Layer 3 can communicate to layer 4. So now your layer 4 should go and communicate to layer 7, because in between that you can see that we have the dashes, right? So that's the very important point, that in one layer you will get the MAC address, in one layer you will get the IP address, in one layer you will get the help that how this layer will go and access the port number and the application. That's the logical order we have that is provided by the stacks. Any doubt in this? Easy, straightforward, right?
No, it's clear for me.
All right. So now let's understand the TCP and UDP. Now, when you are accessing the application, it depends. It depends that what type of application you are accessing. Are you accessing some secure applications, or you are watching some maybe Netflix video, or maybe some uh, online gaming type of thing, you know? So that means that two things are there. One is that is your communication reliable or unreliable? If your communication, if the services you are using is reliable, then you have to use TCP. But if in case your services are unreliable based on broadcast basis, then it will be UDP based, right? So TCP, what they are doing, that they have mechanism, this transmission control protocol, they have the mechanism that they will send the packet and they are getting acknowledgement, sending the packet, getting the acknowledgement. So it's very much like reliable. Why? Because they are based on some feedback, they are based on some acknowledgement, right? And then you have the examples like HTTP, HTTPS, FTPS, MTP, like mailing protocol, etc. They're ensuring that order delivery is there, like, you know, your order is getting delivered and you're getting feedback, you're getting some acknowledgement. On other hand, for fast applications like live broadcasting, live broadcast for matches and some other video applications, some call related applications where you don't want to get delayed, means you want to deliver but you are not worried about the acknowledgement, because services are such that you don't want to wait. So on those services, on those cases, we are using UDP. They are fast because they are not relying on the feedbacks or the acknowledgement, but they do not guarantee packet delivery, order, and the error checking. Examples are DNS. Actually, DNS is using port number 53 with both TCP and UDP, but DNS, DHCP, TFTP, WAP, live streaming. Those are the examples related to UDP, right? So now what I have done here, that a small lab is there. Anyways, today we are going to do one lab. So in the lab, again, we'll go and test that. Here you can see that in terms of reliability, TCP is reliable. In terms of speed, UDP is faster. In terms of overhead, TCP has more overhead because it is connection oriented and it is based on the feedbacks. So like that, some key differences are there that I have put here. Then I'm going to show you one small lab here. You can see the lab topology that you have PC1, a router, and PC2. In our lab, instead of this router, we'll go and use switch number 110. In our lab, we have one switch which is connected with two host system, two PCs. So I will go and connect my device with that to PC. And then what exactly we want to do here, that we'll go and start our lab, we'll go and do the connection, and we'll go and test the TCP sessions, TCP connectivity, right? We'll do that. You can see the full configuration. I am going to show you this configuration. Once we do this configuration, I will explain you everything in the configuration. Then we'll go and test port number 80. I'll show you that within the router, how you can go and test port number 80, and how you can go and test the other port numbers as well. Any port number you can test within the routers. So that I will show you in the lab. Okay. So now let's quickly revise it. TCP, what it is a connection oriented protocol. And if you are using TCP, what benefit you have? You will use for reliable services. Although what is the drawback with TCP? TCP is something that is slow. Why? Because it's based on the reliability. So that's why it's slow, because if any packet will dropped, if any loss of packet is there, then TCP protocol, what it will do, it will resend those packets. Since it will resend, that means that the speed is slow, because it is doing the it is resending the packets and all. Okay, so now what we want to do, that we want to complete one lab. Let me pull my lab devices here, what we want, and let me go and quickly draw one small topology. So I have one router. Assume that I have one router, and this router is directly connected with two PC 11 and PC 12. Now, since it is connected with PC, and we have discussed about this thing earlier, that the interfaces in the router, they are nothing but the gateway. There you have to go and define the gateway, right? So we have an IP schema that we want to configure 192.168.1.10. Suppose this IP is 192.168.1.10 and this IP is 192.168.2.10. And if you have IPs like this, then your gateway will be 192.168.1.1. And this gateway, I'm writing only last two octets here. 2.1, this is the gateway. Now the gateway address that you are seeing here, where you will define over the router interface. So 1.1 here and 2.1 here. This interface. Suppose this interface is E0/0. This interface is E0/1. Understanding this topology, you have any doubt? And this route,
No, I'm good so far here.
yeah, this router, in our case, we have switch 110, which will work as a router as well. So in our lab, the lab that I share with you, these devices that you can see, host 11 and host 12, they are also a type of small router. But if you want to simulate this lab, you want to make them as to work as a host. So what you can do, you do one thing, no IP routing, and then define the default gateway. Default gateway 192.168.1.1, and then go to interface, IP address 681.10 as per the topology. Right, so we will do this here as well. No IP, we don't want routing here because this will work as a host system. This is just an end host machine. We want to configure it on 682.10. So now, first of all, you should ping. So this is your IP, this is machine IP, and this is the gateway address. default gateway. Because I should go to the switch and I should go here. I know that we have E00 where I have to give this IP address. As it is not taking, I should make this layer 3 and then I should go to the E0/. If you do no switch port command, then the interface will work as a layer 3 interface. If you go and use the command switch port, then the interface will work as a layer 2 mode. Now, since we have assigned the IP addresses, why not let's first of all go to the host and ping to the gateway. So for this host 11, the gateway is what? The gateway is 192.168.1.1, right? Which is, you can see, successful. You are getting the ping response, that is we are able to reach. And with this system, what's the gateway address? 192.168.2.1. So what we are doing actually, that we are able to reach to the gateway. From here, I am able to reach to, let me use the arrow. So from here, I am able to reach to this interface, and from here, I am able to reach to this interface. But can I go and ping from 1.10 to 2.10 or 2.10 to 1.10? If you do that, that means you will go from your host to this interface, then this interface, and then this system, right? Like the path will be like this. You will go via the router to reach there, right? So if you go and do the ping 192.168, suppose 2.10, and source is 192.168.1.10. You can see first packet get dropped. That's why you have this dot signal, and then you have 4 successive ping. That's why you are getting this exclamatory sign. Next time if you ping, you will not have any drop. Next time when you are pinging, you don't have any drop. Why? First packet get dropped because they are doing some sort of ARP resolution in between them. So they try to find that with this MAC, what's the IP, where is the gateway, and all those things. So there was some small delay. That's why one packet get dropped. But next time onwards, you can see next time if you go and say repeat for 100 times. If I ping for 100 times, so this is the destination, ping to this destination with the source, SO for source. This is the source. Repeat for 100 times, you will see there is no drop. Packets are going easily because now some of the packets, source and destination, they are cached somewhere. So that's why it is going there. But this is not the test that we want to do. What we want to test here is this, that if I have to go and use the web services here, right? So I can go here to this device and I can enable IP HTTP server, IP HTTP secure server. So what I am doing, I am starting port number 80 and port number 443 in this host, in host number 12. See this host, assume that this is the server, right? And this host 11, assume that this is client 1 or 2, anything. So from client, I have to go and check that can I go and use port number 80, right? So for this, you can use telnet feature 192.168.1.10. 2.10 with port number 8080. Now, if I go and enter, and if you get one message called open, like port is open, that means that port is open, you can access the services. And here I'll go and debug IP packets just to show you IP HTTP all, just to show you this message. It's open. You can see packet cap. We are doing some packet capturing. So this I wanted to highlight to you, that you will see the source. What's the source? The destination. What's the destination? Length of packet. Some checks. Some router type. For us, false. MTU 0. Some checking, right? Some checking. And my purpose. One thing. Debug TCP. TC. It's not there. Debug IP. TCP. Packet. So let's do one thing. Undebug all and debug IP TCP transactions. Just to show you TCP packets. Packet. What other things I have? ECN is there, compression is there, packets are there. I think transaction and packets are more than enough. So you can see this established. Now you can see the TCP packets we are getting, and this actually I wanted to highlight. This is very important. So you can see the source packet. Source is what? 192.168.1.10. And the source port. Source port will be anything in between 0 to 65500, like 650. The well-defined port numbers we have actually. The port numbers, they are lying in between 0 to 65,000, right? And there are well-defined port number, like port number 80 is for HTTP, port number 443 is for HTTPS, uh, port number 53 is for DNS, port number 161 for SNMP. Like that, you have series of port numbers in between 0 to 1000, which is well-defined port number. So when this device is sending their packet, obviously in that packet, then when they are creating the packet, so they will start with any random port number. Those packets will start with any random port numbers. So that's why you can see here this port number. But what is your destination port number? Your destination port number is 80 because you are sending the destination at 80, right? So that's why your port number is 80. And not only that, you can see this fin, the fin, ACK. These are actually the flags. TCP having 6 different type of flags. So you can see all those flags. Fin push. Fin is the push. Some sliding window concept is there in TCP. So you can see the window size. Window size is 4128, 4128, 4128. Then you will see somewhere acknowledgement. See, acknowledgement. You are sending the SYN ACK SYN. You are sending the packet. You are getting the acknowledgement. You are getting the acknowledgement. Right? You are getting the acknowledgements. You are getting, because this is a reliable communication. So that's why you are getting the acknowledgement as well. All right, so I hope that you understood the difference in between TCP, UDP, and how they are working behind the scene. That's why I try to show you in the lab as well. Finally, I can see this is just right. Anyways, let me go out from here and let's continue our discussion. Few examples, you can go and check port number 53, port number 80 and all. Right, we have completed 1.5. If you have any question, please feel free to ask. At the moment, I haven't explained you about IPv4 addresses and what is meaning of addresses and subnetting, but don't worry, we have to understand that. IP addresses, I simply took one example and shown that, okay, 192.168.1.1, 1.2, 1.3, but actually we have to understand the format as well, that why we have this, what is the network piece, what is the host piece, and all those things. In the syllabus, in the CCNA syllabus, that thing will come after this session. So that's why I'm just following the syllabus. And it is good also that anyways we know that what is IP address and what is the format. So later on when we'll go and take the example related to host part and network part and host part, then you will understand a little bit more about the IP address formatting. Till this point, if you have any question, you please feel free to ask.
No, I'm good so far. Yeah.
Okay, all right. So now in 1.6, what exam expect that we should configure and verify IPv4 addressing and subnetting. So for that, we have a small topology. You can see that we have switch 110 that will work as a router. We'll assume that this is one router, or two router, three router. Switch 110, they are connected to switch 101 and switch 102. You can see the connections here. I will go to these interfaces and I'll assign the IP addresses. Now, before going to IP addresses, I should understand the format, and I'll take just 1 minute on this because later on we have to understand this entirely. Let's take one example here and then we'll move. So if you see this particular range 192.168.1.0/24, this /24 is nothing but this is the subnet mask, and this will be, we know that IP addresses, they are 32 bits in size. So this /24 means that you have 8 ones, 8 ones, 8 ones, and then you have 1 2 3 4 5 6 7 8 0. /24 subnet mask means that you have 24 ones and 8 zeros. That's the meaning of this, because this is something like very much human readable. It is in decimal, right? 192.168.1.0, but behind the scene they are in the binary format. When machine will learn these things, they will learn in the binary format. So 192 will again convert in this format. 168 will also get convert in this format. It will be something like 1110000 like that, 192. Little explanation I'll give you later on. But yeah, so your IP address will start from 1.0 and then it will end to 255. So that means how many addresses you have? From 0 to 255 means 256, right? 256. This is nothing but if you go and multiply 2 to the power 8, 2 to the power 8 will give you 256, right? 256 addresses. Why we are getting 256 addresses? Because of this subnet mask is 24, because in last octet you have how many zeros? 8 zeros. So 8 zeros means 2 to the power 8. That means 256. So you will get 256 IP addresses in this, like 256 host addresses in this, right? But in networking, the first address is used as a network address. This is the network address. What is this? 1.0. This is the network address. And the last address that you have, this is the broadcast address. Because what you have in the last 255. This will be the broadcast address. This will be the network address. So these two addresses you can't assign to any laptop, any PC, any system, because this is what? This is network, and this is what? Broadcast. But from 1.1 to 254, you can assign to any system, right? These are the host addresses you can assign to system, but for these hosts you have to define the gateway. So generally 1.1 we are reserving as a gateway address, and then we are assigning the address from 1.2 up to 254. Okay, so like that we are playing with the numbers. So now if you see here,
One question there. What if we need more IP address on that and that's subnet? Can we
so
change the 24 to another
yeah,
so
so
can
make
have
this
more?
0, make this 0. If you make this 0, then this will become 2 to the power 29, 2 to the power 9. If you make this 0, then your address space will become 2 to the power 10. If you make this 0, address space will become 2 to the power 11. So 256 will become 512. Then
Oh, okay.
this will become 1024. Then this will become 2048, like this. So make this 0, 0. So that means this will become /23, /22,
Plus 22, yeah.
/21, /20, /19, /18, like that. This /8, then you will
Okay,
get
yeah,
more
I got it.
address.
Yep.
Okay, all right. But I will explain this because I think this is there in upcoming session. So we'll discuss about this, that how we can get more addresses. We have that, actually we have that topic in upcoming session. So we'll discuss about that. For this lab, you have some IP subnets. So the IP that I wrote here, I should write here 1.0. I should write here the network address as 3.0. 3.0. So here you can see 1. Here I should have 2. Even the IP schema is wrong here. You will get duplicate address if you go and assign such type of addresses. So suppose this is 1.0, this is 2.0, and this is 3.0. Like that will configure in the devices. But if you go, oh, so one slide I left just to explain. But if you go here, you will see that here it is okay. The IP in the sheet is okay. You can follow these IP addresses and schema. And you can see the configuration. Router 1 configuration will go to router 1 is nothing but switch 110 in our lab. Sorry, so router 1 is switch 101. Okay, no problem. I should write here that in our lab this is switch 101 and this is switch 102, like that. So you can go to the interfaces, assign these IP addresses. You can go to the interfaces, assign these IP addresses, and then you can go and check show IP int brief, show IP int brief, show IP int brief, and then you can try pinging from one location to other location, and that will complete the lab that we have. Okay, so let me quickly go and pull my lab. So here you can see that switch 101, and you need the interfaces, how they are connected. Do one thing, default the interfaces first. And we don't know what interfaces we have. So we will go and default all the interfaces. Even we have 2.0 and 2.0. So all the configuration will come here. Do show history. Just take this, default the interfaces. Just take this and default the interfaces and do one thing. CDP run. Run this protocol CDP. So it will tell you that which interfaces are connected how. Now if you go do show CDP neighbor, I will come to know that you will come to know that switch 110 is connected to 102. You can see client server as well. 102, 102. Not showing that how it is connected to 101, but anyways, 102. I just need one interface, right? So it will tell that local, I am this interface, I am connected on this interface. I'll go here to E1/2, we'll do no switch port, IP address 192.168, suppose 1.1, and we have done some IP configuration seems over E00, E01. So default E0/0. I don't need that. Default interface E0/0. I don't need this actually. Now I'll go to E. What was the interface? This. What was the IP? This. Then interface. So what interface I am connected with? The 101. So 102 I am connected with this. No problem. But what about 101? I think that is E1/0. Let me see the diagram. In the diagram, that is there in the diagram as well. You can refer the topology that is in the slide number 1, but that is default interface E1/0 is connected here or maybe here. CDP neighbor, and even if you're not getting this, so manually you can go to interface and you can do CDP run. Manually you can go to interface, you can do CDP run, and then you can check this. Maybe from this side, from switch 101 side, 1/0, CDP enable, and from this side, this is actually 1/2. These things you don't need to do actually, but just I'm showing you that sometimes if you want to search the topology, you can go and utilize these methods to search the topology. Somehow this is not searchable due to some reason, but anyways, no problem. We'll check that. I know that where it is connected. So I can go to the interface, say from my side, this is E1/0, no switch port, IP address 192.168.2.1. Okay, and now you can see do show IP interface brief. And if you want to filter, how you can filter? Include manual. So you can see that we have manually assigned these IP addresses. 10, 12. 10 is connected with switch number actually 101, and 12 is connected with switch number 102. So if I go to interface E1/2, and if I do 168.2.2, I shut 2.1. It's failing. Okay, do so CDP. Let's see. So 1.2 on 102, and what IP we have configured in 1/2. Let's see. Brief. Oh, 1.1. So that means should come configure here like this. And now if you ping, yeah. So how it is, let me quickly draw the diagram, otherwise get issues here. So I have assume three routers, and these routers, they have the connectivity like this, like this. We'll not use this link in between, right? We'll not use this. Suppose we have this connectivity. And even if you're using this link also, I think in the diagram, in the initial lab topology, I have that 6.8. Suppose this is 2.0/24, and this is 1.0/24, and below that will be 3.0/24. Like that will go and configure. 1.0 there. This is switch number 110. This is switch number 101, and this is the switch number 102. So in between 110 and 102, we have done the configuration. So if I go here to switch 110, we will see that this interface is actually connected. So interface E1/2, we can give the description as well, connected to switch 102. And we can check the description later on just to understand that where it is connected. You can see the description, or you can do like this to show. I will show that E1/2. So now we can see that E1/2 is connected to this switch. Then we have one interface E1/0 that we want to give the description, connected to switch 101. This interface connected to switch 101, but from switch 101 side, if you go to switch 101, you have to go to interface E1/2, and that is the description, connected to switch 110, and here you should give the IP address 192.168.2.2, no switch port. First you make this no switch port, and then try to ping to the switch 110. Now it is successful. So this connection here is pingable, it is successful. This is successful. This is successful. Now we have this connectivity 2/0 here actually, 2/0, 2/0 both side. So now I'll go to interface E 2/0, no switch port, IP address 192.168.3. For example 1, connected to switch 102. Likewise, I can go to switch number 102, interface E2/0, first no switch port, IP address 192.168.3.2.255.255.250, give a description, connected to switch 101, and try to ping 168.3.1. So now you can see that all these devices do show IP int brief, and you just wanted to include 10. I just wanted to see the IPs that we have configured. Oops, not 10, include 192 IPs that we have configured. So this is up running, this is up and running, and this is up and running. Right, so this is the lab that we want to configure complete. If you have doubts, you can ask. Otherwise, you can check even the video as well, and even the document as well. Everything is configured in this, and then you can do the ping test. Everything is there configured. Only you have to go and change the interface name. You have to go and search the interface name. That will be new learning for you, that how you can go and use CDP or LLDP to discover the topology, and then you can go and work on this particular lab. Today you can see that we are in day number 5. Till day number 4 I have uploaded the recording in the shared folder. Day number 5 we have to learn these topics 1.7 up to 1.9. 1.7 is understanding the private IPv4 address. Today we are going to learn a little bit more about IPv4 addressing schema, how it is working. Then from 1.8 itself, you can see that we have to learn and understand about IPv6. So IPv4, IPv6. These are logical addresses, and in the protocol stack, they will be at the network layer. First we have physical layer, then we have data link, and then we have internet or network layer. In OSI network, in internet, in TCP IP, it is the internet layer. So we have to go learn about IPv4 and IPv6, but you can see the topics related to IPv6, you have to learn a lot. You have to learn about IPv6 addressing prefixes, their address types. In case you have Unicast, Anycast, Multicast, and then modified EUI, IPv4, IPv6 addresses. Like that, you have to understand everything related to IPv6. So let's start. First of all, it is asking, the syllabus is asking us to learn, this is as per agenda, to learn the private address. So that means there may be some public address, there may be some other type of addresses. So what does it mean by private address? You know, what does it mean by private address? Anyone can answer, please. You know that? What is that?
Yeah, the only ones that can be reached inside of network preparation.
Anyone? Sorry.
Can you hear me?
Yes, yes, your
Hello?
audio is a little
Yeah.
bit. Yeah.
The privates are the IPs that can be reached only inside a network, a corporate network, a local network.
Private, yeah. As name suggests that this is private, like within the
Private.
organization, they are using it, right? So you're correct
Mm-hmm.
that within the organization, people can use such a address, and these addresses are not routable, like they are local to the organization, right? Okay. And suppose if you have to move out, how you can go outside with these private addresses?
You need to go to a public address,
Yeah, so somehow you have to
the
translate the
internet.
address to go outside, right?
Exactly.
So public addresses are, that means routable. They are the addresses over the internet, but these private addresses, they are local to the site, local to the network, local to the company. And suppose if two different locations having private addresses, they need some public address to go out, come in, like to do the routing. But these private addresses, if they want to go outside, they have to do some sort of natting process. They have to do some sort of translation process. That's right. So let's see in the slides. Private addresses, they are defined by the Internet Assigned Number Authority, IANA. Okay, and they are used within a local network without conflicting the global addresses or the public addresses. Now, they are divided into 3 different parts. You can see class A, class B, class C. So what is class A? Class A having subnet mask /8. What does it mean by /8? /8 means the subnet mask, the CIDR value will be 255.0.0.0.0. dot 0. So class A subnet mask will be 255.0.0.0, right? That means 1, 2, 3, 4, 5, 6, 7, 8. 8 times 0, 8 times 0, 8 times 0. If I miss 1 or 2 0 in between, but I just wanted to write 8 times 0. Here we have, I think, only 7. 8 times 0, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 8 times 0. So 8 times 1, 8 times 0, 0, 0. This is the subnet mask. That means from this, with this type of subnet mask, how many host addresses you can get? So you can get the host addresses 2 to the power 24. That means you can say approximately this much, 16 million something, right? Number of host addresses or number of addresses like this, 2 to the power 24. Likewise, if you are in class B, here you can see class B, that means subnet mask, you can see 255.24000, right? 240. So how we can go and present in binary? So 255, suppose 255.254.000, that's mean 11111111, that means 255, then 1111 and 11. How you can make 254,
Zero, yeah, there.
right? Little bit math is there. These are 8 zeros. Maybe I'm writing 7 0, but these are 8. So here you can see that from here, how many hosts you will get? You will get 8 plus 8 plus 1 means 2 to the power 17. Number of hosts will be 2 to the power 17. Actually, number of IP addresses will be 2 to the power 17. Number of hosts will be 2 to the power 17 minus 2. You are not taking the first address and the last address. First address is the network address. Last address will be the, I'm doing something wrong here. 8 plus 8, how it is? Oh no, I'm not doing anything wrong here. Maybe something missing here. Anyways, so this is what? This is your class B. So class A, class B, then class C. 255.255.0.0. That means 8 plus 8. Maybe something is missing here. 8, but this is taken from some books, some textbooks. So maybe this is okay. But anyway, class C, you can see that it will start with 192, right? 192, 168.255. Basically, it is starting with 192, and that's the range you have. Let me quickly go and check class A, class B, class C, private. So let me check in Google. Okay, so I just wanted to double check this. This is correct. This is from 192.168.255.255. This is 172.168.255.255. 172.31.255.255. This is from, wow, this is from actually 1.000. Oh, this is correct. Private range is 10.00, 10.2. Yeah, this is correct. These are correct information. So again, if you can see here, if we have subnet marks like 255.255.00, that means 8 times 1s, 8 times 1s, and then 8 times 0, 8 times 0. Number of hosts will be derived as 2 to the power 16. Right? So like that, you can go and derive the number of hosts. Here, the subnetting that I have done is actually wrong. That's why it is, I'll correct that, no problem. So let me correct this, because sometimes I'm uploading these videos to YouTube or some other places. So someone should not go and laugh on us what we are doing. Okay, so this is your IP. See, generally how it is. when you are creating the table, right? Table, this is something like this. Suppose 1, 2, 3, 4, 5, 6, 7, 8. That means this is 2 to the power 8. Assume that this is 2 to the power 8. This is 7, 6, 5, 4, 3, 2, 1, right? That means if you have 1, 0, 0, 0, 0, 0, 0, that means that value will be how much? 2 to the power 8. That means 2, okay, let me calculate. So we'll understand more from here. 2, I am doing today. Let me go back here. Let me try one more time. 1, 2, 3, 4, 5, 6, 7. Okay. 1, 1, 2, 3, 4, 5, 6, 7, 8. So if I have number, this is what? 256, right? How it is 256?
Yep.
Because this will be 1. Why with this is 1? Because this is 2 to the power 0, right? This is starting with 0. This will be 2. This will be 4. This will be 8. This will be 16. And I need some more space here. Okay, let me try one more time. From here, I need some space. 1, 1, 1, 1, 1, 1, 1, and 1. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Now this will be 1, this will be 2, this will be 4, this will be 8, 16, 32, 64, and 1 to 8, right? So that
Yep.
means that number I was writing, it was not 250. This is 1 to 8 actually. Earlier. Okay, anyways. So if you have 1 and all zeros, what will be the value? If you have something like this, right, this will be 256, right? If you have 1, 1, 1, 2, 3, 4, 5, 6, all 0, that means 256 plus 64. Sorry, my bad. This will be 128, right? And then 128 plus 64, how much this is? 192, right? And suppose if you have 111, 1, 2, 3, 4, 5 times 0 plus 32, 2 to 4, right?
2, 2, 4, yep.
2, 3, 4, 1, 2, 3, 4. How much this is?
240.
240, 1, 2, 3, 4, 5, 1, 2, 3. This will be 248, right?
248.
3, 4, 5, 6, 0, 0. This will be
52.
52. Yeah, 1, 2, 3, 4, 5, 6, 7. This will be 2, 5,
4.
1, 2, 3, 4, 5, 6, 7. This will be 256, right? 256. 255, sorry, right?
255, yeah.
Okay, so likewise, we have this 1 and 0, they are getting calculating. And after that, if you are moving, you'll get 256. So point here is this, that if you have such type of CIDR, earlier 240. So that means how it is. So if I have this one here, this will be 1, 2, 3, 4, 5, 6, 7, 8. And then 240 is what? 1, 2, 3, 4, 1, 2, 3, 4. And then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This is the correct value for 255.240.0.0. And from here, how many zeros you have? 8 plus 8, 16, 17, 18, 19, 20. So the correct value was not 2 to the power 17. That value is 2 to the power, that will be the power 8 plus 8, 16 plus 4, 20. So whatever value will come, I think this will come this much. So that's the value actually for this. Anyways, I think you understood this maths, right? So suppose
Yep.
if I have subnet mask 255.252.0, so 250 means how many address can be derived? 111111. Suppose this is 8111111181, and then 252 means 1 2 3 4 5 6
6
0
1.
0.
Yeah, 100.
1 2 3 4 5 6 7 8. So that means number of hosts will be number of zeros. That means 8 plus 2 10. So 2 to the power 10. That means that 2 to the power 10. So you will go and add few more ones here. Suppose one here and one here. That means 256 and then 512. So that means number of hosts will be 512, right? Then suppose if we go and remove one extra one here and put 0, so number of hosts will become 1024. Likewise, the number will go and increase in this direction. All right, so that's the significance we have with the subnet mask. Subnet mask, that means you are increasing the number of hosts, and you know the formula for number of hosts is that total value minus 2, because you are not taking the first address. You can see you are not taking the first address and the last address. So the first valid host will be 192.168.0.1, and last valid host will be 192.168.255.254, just before this one, 254, right? So first one and 254. But total number of IP addresses you will be this first as well, last as well. Okay. So this is the private range. I hope that you understood this. Now to convert this private to public, what you are doing, you can go and do the NAT process. NAT process means this all these internal IPs can be converted to the external IP with some natting. So what you can do, that obviously NAT is not a current topic, means you can take these addresses, and these addresses you can translate to outside. Assigning these addresses, we have learned this in our previous lab, that you can go to the interfaces and you can assign the IP addresses. Go to the interfaces, you can assign the IP addresses. But these are the private addresses. If you have to go outside, you have to do some sort of translation over the WAN interface, and then only they can go outside. At the moment, they are part of the LAN gateway. So far, good? Okay.
Yeah, this goes there. Yeah.
All right. So,
Hey, Ganesh,
yeah.
just one question.
Yes, please.
Can you go back to the slide, to the previous slide, where you found no, the other one, sorry, this one. And the first one, you say that the number of addresses is 2 at 24,
Yeah.
24.
8 plus 8 plus 8.
Okay. And on the second, on the B, you say it's
This will
2
be
at
8 plus 8 plus 8 plus 8, 16 plus 4. You can see
plus
number of
4.
addresses are this much, yeah. Because 240, that means that we have just checked the math. That will be 240. Yeah, you can see here.
Zero.
Yeah, so four zeros. That means
Okay.
8 plus 8 plus
Eight,
4.
eight. Okay. And the third one
Third
is
one is 16 flat. This is straightforward.
okay.
255
Okay.
2500. That means 16. That means 65,000 hosts we can get.
Got it. Okay. Thank you.
Okay, so now we have very important topic related to IPv6 addresses. So first of all, in this agenda, we have to learn about the IPv6 address configuration, addressing and prefixes. Now, IPv6 addresses are 128-bit. You can see 128-bit. Earlier, the address that we have learned IPv4, that is 32-bit in size, and they are not fulfilling the address space. So that's why we were looking for some higher address range, and that's why we have this giant IPv6 address schema. You can see below few examples, and this is actually very big. 128-bit means how many millions we can get as a IP address. It's a huge addressing scheme because adding only one bit will add so many numbers, and 2 to the power 128 will be a very big number, very big number. So here you can see that we need the IPv6 addresses because the IPv4 addresses are getting exhausted. It's almost exhausted, and we need some better, bigger IP schema that we can go and assign to all the networking devices. Nowadays, so many different devices are there, not only Cisco routers and switches. There are so many different devices where you can go and assign the IP addresses. Nowadays, I think all those devices, they want to connect to the network, like IoT devices or medical handhelds devices and biomedical devices, and there are so many. If you go to any industry, they have devices that can be connected to the network, because if they are part of network, then you can do some automation to those devices. So nowadays, almost all the devices you can assign some IP addresses, a smartwatch, smart TV, you know, even a fridge, even house also, like, smart homes are there where you can assign some IP, smart cameras and all those things are there. So that's why we need some better, not better, but you can see that bigger, bigger IP schema, and where we can assign the addresses. So that's why we have this IPv6 addresses. Now, the point here is this, that if I know IPv4, can I get understand this IPv6? Answer is no. IPv6, the nature of IPv6 address is very different. Like, assigning the private addresses is different. Their global, like they also have public and private addresses. That is very different. They have their multicast address. That is also very different. You know, I should go and create one chart like IPv4 versus IPv6. What I will do, I will add that chart in this presentation for next session, that IPv differences in between IPv4 and IPv6. So then you will understand more about IPv4 limitations and comparison with the IPv6. So we have some point, like, we can go and correlate and understand a little bit more about these addresses. At the moment, no problem. Let's just start IPv6. You can see this number. Can anyone memorize such type of addresses? No, right?
No.
Well, it's 2001, O, B, D, B, A, B, C, D. So like that, it's a big number. At the moment, you just focus on this portion, 2000, 2001, and these numbers. So if any address that will start with 2000X, that will be actually part of IPv6 address. They are termed as a global unicast IPv6 addresses. Now, in our lab, suppose if we go and assign the addresses, so let me go and Before going any further, let me go and pull the lab devices where you are. Okay. What was the interface, connecting interface? Okay, that is E01, E01. So if I go directly to E01, now let me do this thing. Show IP into brief. Don't have any address. E01, E0. Okay, this has some IP address like this. Show run interface E01, include 10. See, this is the IP address to E01, right? And oops, I can go to interface E0/1, IPv6. I can do IPv6 enable to this interface. And to show IPv6 interface. So instead of IPv4 address, you can type this command show IPv6 interface brief to see the IPv6 addresses. Now you can see we haven't assigned this address FE8011. Automatically I can see E01, right? E01. I haven't checked, even I can see all those interfaces, they are getting some addresses, but I haven't assigned. Manually I will go and assign this as well. But you can see that one address FE80 colon colon 8. This colon colon means, what does it means? It means the trailing zeros. So suppose if we have IPv6, you know, IPv6 address, when you have to go and write the IPv6 address, that will be suppose 128, right? 128 bits. That means if I go and divide into 8 different parts, so 16 into 8, how much it is? 16 into 8, 128, right?
Yeah, 120.
120. So that means that 16 bits. So 16 bits and then 16 and then 16 bits, like, you know, 16 bits, 16 bits, 16 bits, 16. 1, 2, 3, 4, 5, 6, 7. 16 bits. What about IPv4 addresses? It's like 32 bits. Like it was 8, 8, 8, 8, like that, right? 8 bits, 8 bits, 8 bits. Not the IP address. The 8 bits like 0 or 1 or combination 0, 1, like that. So it is like this. But IPv6, you can see 16 plus 16 plus 16 plus 16, 8 times. So that means if I have any address, suppose I have an address 2001. Now this is in hex. This is in hexadecimal. And suppose I will use 0.0.0.0.0.0. So 1, 2, 3, 4, 5, 6, 7. So this is one example related to IPv6 example. This is in hex. Hexadecimal, you know, hex means if you go and convert this hexa means 2001 means 000, sorry, 0010 is 2. 000 is 0, 000000001. This is what? 2001 in hexa. So that means 4 plus 4 plus 4 plus 4, 16 bits. Because one portion of IPv6 is how much? 16 bits, right? Now, any doubt in this part? One portion is how much? 16 bit, because total it is 128 bits, right? Now, we haven't assigned this address FE80 colon colon 11. This means colon colon means number of zeros. So here how many part portions you have? Only 2 portion, right? So that means this will be FE. If you go and write it in, if you expand this 0, 1, 2, 3, 4, this will be like this. This is third part. This is fourth part. This is fifth part. This is sixth part. 1, 2, 3, 4, 5. This is seventh part, and then 0, 0. Just wanted to say. You got my point. So FE80 ::1 : means that you're removing this number of zeros. So that means
Yeah.
this is exactly like this in full form. In short form, this is : :11. But in longer format, this is FE80 and then number of zeros like 16 0, 16 0, 16 0, 16 0, 16 0, 16 0, and then 001. Now, if I have one address, one IPv4 address, let me show you that generally how we are doing in organization, because it's very difficult to memorize the addresses. So my IPv4 address over this interface, you can see 10.199, right? So if I have to go and derive the address, IPv6 address, how I will do? I will do this like 2001 is common. You have to give this. Then I can do like this 10. See 0010 and then 001 and then 0099 and then : :1 or : 0099 : 1 like this, or better 0099. So we can see this now in short form. This will be 2001 : 10 : 1 : 99 : 1. So you can see this semicolon and these two semicolons. This is nothing but zeros, number of zeros. Like if you have 3 consecutive number of zeros, then it will be represented by : like this. Is number of zeros. So for example here 1 2 3 4 5. You have only 5 parts. That means this : means 3 times zeros. 0 0 0 0. Right? That means it will be something like this. The full address will be, let me try to write full address so you will understand this. Full address will be 2001 0010, then 0001, then 0099, then 000, and 000, then 0000, and then 001. So this is the full IPv6 address, but if you want to short it, oops. Oh, 1 0010 0001 0099 0000 0000 0000 and then 0001 1 2 3 4 5 6 7 8. Now shortcut. First of all, you can remove the early 0. You can't remove the 0 coming after 1, but 0 coming before any digit you can remove. So it will become 10, then become 1, then become 99, then 1 2 3 4, then 1 2 3 4, then 1 2 3 4, then it will become 1. And since you have zeros, right? So you can short this address : So you can see the shorter form of addresses, how we can go and make the shorter form of the addresses. Any doubt in this? It's okay, right?
Yeah, clear.
All right. So over this interface that we have, this E0/1, let's go and assign the IPv6 address. Like you can go and assign the IPv4 address, you have to give IPv6 address, and 2001 10.1.99 colon colon 1, but you have to give the CIDR value as well. I'll explain you all these things. Like this I can assign, and I can go to R20 R12 0/1 IPv6. Let's see. Do show IPv6 interface brief. I can say link local addresses are already there. That means IPv6 is already enabled. But over this interface E01, we'll go and assign the point-to-point address like this. This 64 is, you know that what does it mean 64? How many bits you have? You have 128 bits. So /64 means what? Number of hosts will be 2 to the power 64. That is remaining. /64 means 64 ones. Right? If you are writing, say for example, let me explain you about the CIDR value. See, if we have in IPv4, if we have 255.255.255.0, this is the subnet mask. In CIDR, what it is? 24, right? CIDR means number of ones. So 255 means 8 plus 8 plus 8. That means its CIDR value is 24, right? So number of hosts will be how much? Number of hosts will be number of zeros, means /8 means 2 to the power 8, right? So likewise, if you have /64, what does it mean? /64 means 64 ones. That means number of zeros, how much? 64. That means number of hosts will be 2 to the power 64, right? I'll write this thing. Let me. So either it's IPv4, or IPv6. The CIDR value, classless, what is this? Classless domain representation or something. CIDR values. This CIDR value is nothing but the number of ones. Number of ones. Right? Number of ones means what? Number of ones, that is the mask. Number of ones means the mask. So if in IPv4, if I have 255.0.0.0, what is the CIDR value? CIDR value, classless interdomain routing, right? The CIDR value will be /8, right? But a number of hosts will be, or number of total IP, should write IP. Number of IP will be how much? 2 to the power
2 to the power of 32.
24.
No, 24.
Number of zeros, 8 plus 8 plus 8, right? Like if your subnet mask is 255.255.255.0, so that means that how many zeros you have? Sorry, what is the CIDR value? /24, right? So number of IPs will be 2 to the power 8. Right. Likewise, in IPv6, if we have /64, so that means number of IP will be 2 to the power
64.
64, because this is 64 plus 64, 128. Like in IPv6, if you have 128, what will number of IP? 2 to the power 0. That means 1, only 1, right? Here also, sometimes we are giving subnet mask 255.255.255.255. That means what will be the CIDR value? 32. So number of IP will be 2 to the power 0, that means only 1, right? Loopback addresses, when we are assigning the loopback address, let me show you here. If I go to this router and if I show this do show run interface loopback 0, you'll see loopback address 128/32. These are what? These are nothing but the one address, only one address, that is /32 or /128.
Rajneesh,
Mhm.
question. Could you
Yes.
please, I don't know if you already did it. What is exactly the loopback? The loopback interface or loopback IP? Can you explain that?
Yeah. Uh, so I will hold this question for when we'll start the routing. You will understand more about this. In short, I'll give you explanation in short.
Okay.
But later on, I will explain you more about this loopback address. Suppose this is your router, and in this router, suppose you have one interface, two interface, three interface, right? Now, what will happen if these interfaces will go down? These are physical interfaces. They may go down, right?
Okay.
Or there may be chance that at a time only one interface or two interface will go. Not all the interfaces will go down. So these since these are the physical interfaces, they can go down. But there is one concept of loopback interface, irrespective of physical interfaces are going down. Until unless your router is up, loopback interface will be up, right? Because it's a logical interface. Generally, these are the logical interfaces representing the system, representing the router. And these logical interfaces, you can go and glue all the physical interfaces. That's the concept actually, but I'll explain you later on more about this. There are use cases related to loopback addresses, why we are using it and all. Loopback interfaces can be glued with n number of physical interfaces. Okay, but we'll check this later on. All right, so far you're able to understand the subnetting, the side annotations, the IPv6 address, how we can short down the addresses and all those things, right? So what we have done, let's see, that we have assigned IPv6 int brief, the IPv6 address. You can see that we have assigned the IPv6 address. And likewise, we can go and ping the IPv6 address to the remote side. What is the remote address? So my address is ::2. The remote address is ::1, and you can see that we can ping it. Oops. Likewise, you can go, what I'm doing, you can go and do IPv6, or we can trace route IPv6. Oh, trace route IPv6, and if you want to trace the path, all this is just the next hop. Right, so we have derived some new IPv6 schema in our lab. See, we have one small lab topology that we have router 11 and router 12, and they are connected with over the interface E0/1. So we have router 11 and we have router number 12, and they are connected over the interface router 11, and you can see that router 11, router 12, and they are connected over interface E0/1, E0/1, right? And on these interfaces, we have assigned the IPv6 address such as 2001:10:1:99:1, and other side the address is ::2. with /64. Likewise, you can ping point-to-point addresses. You can go and ping point-to-point IPv6 addresses as well. Any doubt understanding this? Clear and straightforward, right? So let me go here to the slide deck. I should clean this. Okay. So let's understand IPv6. IPv6 addresses. You can see here that you have global unicast addresses that will start with 2000::3. Then you have link local address that will start with FE80. Link local addresses are very much like MAC addresses, like local to the interface. And then you have one local unique global address, ULA. ULA as well, that will start with FC00. That is very much like IPv4 private address. They are used for local communication within the site. This is IPv6 private addresses. If any address will start with FC00, that will be IPv6 private address. This is IPv6 MAC address. This is IPv6 routing address. Global, link local, unique. So how you can go and enable IPv6 unicast routing? You have to give this command. So IPv6 will get started within the routers, within the switches. Then you can go and assign the addresses like this. We have assigned one of the address 2000, and then ours is not DB8, but ours something different. And then the link local address you can go and assign like this. FE80::1 and then the link local keyword. No shutdown. Like that, you can go to router 1 and router 2. You can assign the addresses. Then you can go and check the interface. So IPv6 interface will tell you what is the link local address, what is the global address, and what is the MAC address. I will come to the MAC addresses as well. You can go and check the route as well. When we'll do the IPv6 routing, we'll understand more about the routes. You can do the ping and trace route that we have done. Then if you want to perform the lab, you can perform the lab. You have two routers here. In these two routers, you can go and assign the IPv4 addresses. Likewise, you can go and assign the IPv6 address FE80::, suppose 1. What is the CIDR value? No need to give the CIDR value for link local. Simply link local. Do show IPv6 interface gig E0/1. So you can see that what is the global address. This is what GUA, global unicast address, GUA. Then you can see some join group. This is for multicast. Where is my, let's do like this, to show IPv6 int brief. So you will see that we have the 01, we have this link local address, and we have the global address, right? So you can perform the lab over the router, actually in our case, router 11 and router 12. You can go to the E0/1 in our lab. The interface is E0/1. Go to one interface, do these configurations, and you have multiple interfaces. You can assign these addresses, and other side you can assign these addresses. And then you can ping and trace route, ping and trace route. That is the small lab we have, right? That's the small lab we have. You can perform the task. It will take hardly 15-20 minutes. But if you are doing it first time, understand the formatting, the subnetting, the trailing zeros, the leading zeros, the colon, twice colon, all the use cases. You can watch this video. This is interesting, where we have discussed about the subnetting, siders, all those important things. And then you can perform the lab. The next, yeah, you have any question?
Yeah, I have one. I
Yes.
know that the IPv6 also has security features over the IP4. Is that true? Or, and if so, how is used? Or,
Yes, so it has the security feature. We will discuss about that security feature. If it is in the blueprint, but surely it is there in the CCNP blueprint and even CCI blueprint, that how IPv6 providing the security, that it has different type of options related to security, but I, I don't know if it is in CCNA level. I need to check. You want me so I can add those things, security
I
feature.
mean, if it was just a question because I was not sure
Yeah,
if that was
yeah,
true or not.
it is true that we have security
Okay.
features related to DHCP addressing and other, like, RA guard and IPv6 guard, and those features are there related to IPv6. Yes, that's true.
Okay.
Okay, all right. So let's see. This is very small topic. In IPv6 addressing, you can see formats, like you have three different options. It is there in IPv4 as well. Unicast, Anycast, Multicast. Unicast means unicast, like one-to-one type of thing. You can think like this. Addresses that will go and assign to the interfaces. Addresses can go and assign to the interfaces. That is unicast. Unicast, you have global unicast, unique local unicast, link local unicast. So what does it mean? Just now we have discussed that IPv6 addresses having three different options. Here you can see global unicast address that will start with this. Link local address, very much like MAC addresses of physical address, that will start with FE80. Unique local address that will start with FC00::7, like that. So this is related to IPv6 unicast addresses, or oops, IPv6 unicast addresses. So unicast global, unicast unique local, unicast link local. But we have anycast and multicast addresses as well. But anycast and multicast is a technology. Anycast means one nearby, like one to nearby source. So suppose I can give you a better example than this. Suppose you are in somewhere in your location and you will go and open, suppose if you will go and try to access Google DNS server. So in your case, you will go and use your nearby DNS server, although the IP address for DNS is 8.8.8.8, 8.8, everyone. So I can go and ping to IP address 8.8.8.8, that's the Google DNS IP, and you can also ping. But the reply you will get for this IP, that is from nearest server that Google has in your place, and I will get a reply from the nearest server with the same IP that I have nearby in my place. So anycast means near to the source, near to the something. So that means that system may have same IP at different locations, but the response you will get who is nearby source response you will get. This is a technology called Anycast. So in your company also you can think like you have different locations, but you have same sort of DNS servers or maybe IPAM servers and local host servers. So if some query is going, it will not go to the global destination, global data center, but it can go to the nearby server and it will get responded. That's the Anycast. Let me give you the Anycast example. Unico. So this we have discussed. Anycast, yeah. Here you can see. Anycast addresses are assigned to multiple interfaces, typically at different nodes, and are used to route the data to the nearest or the best destination as determined by the routing protocol. The same packet is assigned to multiple devices. When packets are sent to Anycast address, they are delivered to the nearest. Whoever will be the nearest, they will response. So that's the Anycast, right? Same IPv6 address, who will be near, he will response. Now, then we have the multicast. Multicast means one to the group. One to the group. That's the use of multicast. So multicast addresses are used to deliver packet to the multiple interfaces, typically within the same or the designated multicast. So your query is going to one group. That will be the group. One to the group. One to group is multicast. One to one is unicast. One to many is multicast, and one to nearby source is anycast. So unicast, multicast, anycast. These three technology we have. Anycast, unicast one to one, multicast one to group, again let me repeat. Unicast one to one, multicast one to group, and anycast one to nearby. This is one to nearby, this is one to group, and then you have one to one, that is unicast. These three technologies we have. Now here you will see that the multicast address will start with FF00::8. That means one of the example FF02::1, that is for local network segment. But this thing will come again and again to other places as well. So all the routing protocols, they are also using multicast, like EIGRP having some multicast address, HSRP, VRRP, they have some multicast addresses. The OSPF having multicast addresses, So we will really understand that multicast means one to the group, nearby group. Then finally, we have one topic related to modified EUI 64. Modify EUI, that means universal local or something. This address is derived from MAC address. So suppose if we have one MAC address, suppose I have one MAC address, and from that MAC address, if I have to go and derive the IPv6 address, so that will be EUI 64 technology. What does it mean? Let me quickly show you this. Suppose I have one MAC address. You know that MAC address length is 48 bits, right? 48 bits. And I should go to that slide where we have this. Okay, so let me show you this 48 bits from MAC address, how you can go and derive the IPv6 address. Do I have example here? Yeah. So MAC address, this is in 16 plus 16, but I will explain that. 1, 2, 3, 4. So from MAC address, if we have to derive 64-bit IPv6 address, what they are doing, they are putting some values in between. They are putting some value to derive this address. 24 bits will be put. So if you add 648 plus 24, how much it will be? 64, right? So you can see that EUI 64 addresses are like this. What they are doing actually, they are putting in between, they are putting FFFE. So that insertion of, have I mentioned that anyway?
48 plus 24 is 72.
64, right?
No, 72.
This is 72 or something. How much? Okay, no problem. Yeah, you're right. Will not go and put, actually we'll go and put 48 plus 16 will be 64, right? So we are putting 16-bit of something like, some numbers in between, that is FFFE. You're right. Okay, I'll explain this, no problem. Just a second. I need one place where I can write. Here it is. So you have 48 bits of MAC address, 48 bits of MAC, and you need to derive 64-bit of IPv6 address, right? So that means how much you need to add? You need to add 16 bits, right? So how this mechanism is telling that 48, split it into 24-bit plus 24 bits, right? So 24 plus 24, and then after 24-bit put FF, and then FE, and then 24 bits. Like that it is telling. Okay. So suppose if I have one MAC address, AA, BB, CC, DD, EE, FF. You know, 4 plus 4 plus 4, yeah. So 1, 2, 3, 4, 5, 6. I need to add more, right? So let me give better example. Say, you know, MAC addresses are 48 bits. 48 bits, if you divide into 8 part, how much it will be? 8 into 6, right? And now we are not doing networking. Today we are doing mathematics class. So 8 into 6, how much it will be?
Yeah, it
48.
is
48.
part of. Yeah.
So that means that 6 portions I need to write. So okay, so suppose 0 0, suppose 0 0 or 0 0 will something will not solve. It's too easy if I write all 0 0. Let me do something like AA is okay, and then AA, and then BB, and then BB, then CC, then CC, and then GG, then G. So this is, you can see one MAC address. So that means that you have 8 plus 8 plus 8 plus 8. So 8 plus 8 plus 8 plus 24, right? So you have to split this in 2 parts. So I'll go and split in 2 parts. You can see 24 FE 24 like this. So if I split into 2 parts, you can see 8 plus 8 plus 8 AA, AA, BB, and then I'll put FF and then FE. Then what is remaining? CC, CC,
CC,
sorry. Oh, 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 oh.
CCDD.
This is actually wrong example because this is 1, 2, 3, 4, 5, 6, 7, 8. I need only 6 portions. No problem. 8 into, we'll do one more time. No problem doing again. AA 6 only I need. BB, CC, about DD, EE, FF. FF is not a good example. So we'll start with 0, 0, AA, BB, CC, DD, EE. Now this is good example. So you have total 6 portions of 8 bits. Now let's split it. AA 0, 0, then AA, BB, and then FF. Then FE, then CC, DD, E. And if you write in IPv6 format, 0, 0 colon AA colon, no, like this, 0, 0, 0, 0 AA colon BB, FF colon FECC colon DDE. 1, 2, 3, 4, yeah. 16 plus 16 plus 16 plus 16, that is 64 bits. So you can see this is the derived EUI addresses, right? So you can watch the recording, everything we have recorded, and you will understand more and more about this. So if I go here to the last slide, we have derived EUI address, how we have done the derivation. You can see that we have derived that address. If I can go back, I can show you this, right? We have derived this. And if I have one slide where I can show you this, you can watch the recording and take the snapshot, right? How we have derived. And you will understand. Actually, if you do one or twice, you will understand that how we have derived the addresses. Okay, so this was the EUI address, and actually I'm following the agenda that we have. So what Cisco has done, they have splitted the courses in CCNA, CCNP, and CCI. If you go to CCI, IPv6, like in CCNA also you have IPv6, in CCNP also you have IPv6, and CCI also you have IPv6. So they have taken the complexity and they have divided that in different exams. So that's why we have in CCNA, we have to understand this much because this is basic. So you can understand all those things. But if you have good basic understanding, then you can grow better. Basic understanding should be good, clear. Then you can, you know, learn the advanced things and all. So now you can see the summary. We have IPv6 unicast address, global in unicast addresses, you have global unicast address, you have unique local, you have link local. Then you have IPv6 Anycast, then you have IPv6 multicast, and then we have modified EUI 64 that can be derived from the MAC addresses. All right, I think we have little bit extension today, but we have completed the session. If we have any question, please feel free to ask. Thanks for joining. Day number 6, we have so many topics. You can see list of topics here, starting from 1.10 up to 1.13. In that also you have sections and subsections. Okay, so let's start one by one. 1.10, verify the IP parameters within different operating systems like Windows, Mac OS, Linux. In Windows, what we are doing, you can go to the command prompt, typing CMD, and then you can do IP config. So you can see that what is the IP address, DNS, gateways and all. And if you do ncpa.cpl, so your network configuration page will come where you can go and check your virtual NIC cards, your physical NIC card, wireless NIC cards, Cisco, AnyConnect, like AnyConnect NIC cards. Those things you can see. Now, if you want to check more, you can go and double click. You can see the SSID name, the IPv4 address, IPv6 addresses. Now, if you want to check more, you can go to the properties and then you can go and change the, you have option to change the properties as well. So now from here, you can scroll, you can go to IPv4, IPv6. We don't have IPv6 here. I can go to IPv4. If I am here in IPv, you can see we're getting IPs directly like from DHCP servers, from the router that I have, internet router that I have, DNS also I'm getting automatically. Like that, you are getting all those things. If you want, you can right click and then you can go to the properties. The same page you can go and open. And then you can check all those parameters. Apart from that, you can do right click, you can check the status. Within the status, it will tell you that what is the IPv4 connectivity and all. You have this detail button, you can check the IP that it is getting and all those information. Now, this is in the GUI mode, right? Like you can see that you can go to Windows, you can use ipconfig, and then you can check these parameters like IP, subnet, default, DNS. From the GUI mode, you can go and check the control panel, network sharing. So you know that bottom here, you have this control panel. Then you will see the network sharing on directly. Also, you can go and click here. See this wireless network, you can just go there. You can see this network and internet settings. And from there also you can go and check the parameters related to your network and settings and all those things. But generally what we are doing that if we want something, we'll go to command prompt and we are running ncpa.cpl, this command. And then we are getting that network. You can see control panel, network connections, and then you can go and do the changes if you want in the Windows. But what about
What is the
Mac?
command? Can you can paste in the chat the command?
Yeah,
Because only for
that
us.
is ncpa. So first search CMD, like open the command prompt and then ncpa.cpl. That's the command. Okay. Then what about the Mac OS? If you are working in Mac OS, you have option, you can go to the application utilities and then you can go and type ipconfig, press enter. So here you can see that these are the commands for Mac OS to get the IP addresses information, IP config, or if you are specific to certain interface, you can go to IP config, get interface address EN0, Ethernet 0, like that you can go and check, right? So, and then in the GUI, go to preference network, and then you can go and check the network interfaces, go to TCP IP tab, and you can check the network details. In Linux, how we are doing? In Linux, obviously, I will show you later on when we'll do automations and all those things. So we need some Linux servers for our automation for few of the sessions. We need Linux command line interfaces. So it's actually easy. You can either type if config or IP plus IPA, A for address. Then it will tell you the details about the interfaces and IP addresses over the interfaces. These details you'll get. Interface net mask gateway in the Linux machine. So it's easy and straightforward. Mostly you can see IP config we are using or IPA you are using in the Linux system. Okay, so that was the expected section. It's easy only that you should know that how you can go and check the IP related parameters in Windows, Mac OS and Linux. Here you can see the summary, ipconfig, ipconfig interface address, interface name, ipconfig, IPA. These are the commands that we are using in different platforms. Any doubt in this? Easy, straightforward, right? No problem. Let's move on. Now we have to understand about the wireless technology. Wireless technology and a few of the things within the wireless networking, such as that what is non-overlapping Wi-Fi channels, what is SSID, what is RF, what is encryption in that wireless networking. Now, wireless networking is what? It's something that you have AP, access point. So how it is? Let's try to understand first of all this wireless networking in 5-10 minutes, and then I'll explain you those topics. So what is happening that you have some wired backbone. First of all, you need some wired, something solid behind the scene. So you have a wired backbone, and with this wired backbone in this network itself, suppose these are the 3-layer architecture related to switching network. This wired network, you will find that WLC, wireless LAN controller, WLC will be connected somewhere. This is the controller. Now what is happening with this network? Somewhere with the access switches, so suppose this is core switch, then we have pair of distribution switch, and then we have the access switches, and with these access switches, suppose you have your APs connected. Suppose this is my access point, and we have the connectivity. Now you have connectivity, you have connectivity. This is core. This is core. This is distribution. This is distribution. And this is suppose access switch. This is suppose access switch. And then you have access point. Now with this access point, obviously you have wireless network. You have some PCs that they are getting information from these access points. So suppose these are the wireless PCs. Those are connected. Those are connected with the APs. So let me go and connect APs and these APs. Like two subs. I don't have the dotted lines. I just wanted to use some other symbol for the wireless connection. So let me go and use this. Suppose this is wireless frequency. They are connected. So this will be the overall architecture. Now, these PCs that you can suppose these are Windows PC. These PCs, they need to connect to some network. Right? These PCs need to connect some network. That means these PCs also have the antenna. The arrow that you are seeing here in the AP, they are nothing but the transmitter. They will work as a transmitter, but you need some sort of receivers as well. You need some sort of receivers. Someone is transmitting and you will receive, then only communication will complete, right? So you need in your laptop, in your workstation, you need wireless Ethernet card as well, right? So my laptop having wireless Ethernet card. So when someone is transmitting some network, I can go and receive it, right? So the network that these access point they are transmitting, they are nothing but SSID. I'll come to that, but they are the SSID. They are transmitting the SSID, that is the network. And then as a PC, as a laptop, I have the NIC card, I have wireless NIC card, I can go and receive that network. So both having antenna, this also having antenna, this also having antenna. Antenna means that they can transmit and receive. Antenna can transmit and receive. So I am telling that, okay, in my laptop, I have antenna which is transmitting. Yes, you can create a work group within laptops as well. One laptop can work as the access point. Other laptops can go and receive the network from one laptop. Like that, you can create a work group within the laptops as well, because they can transmit as well, but their range will be very small. Okay, so when you are transmitting the network, then you don't want to overlap the network. So you will see that networks that they are transmitting, they are within some channels. They are following some regulation rule that according to this bandwidth spectrum, obviously some bandwidth spectrum should be there. So in that bandwidth spectrum, they can transmit, and that spectrum that we have, in that also you have some ranges like 5 gigahertz, 2.4 gigahertz. We'll check that in upcoming slide. But behind the scene, these things are happening. Someone is transmitting, someone is receiving. So what is the networking piece here? Networking piece here is this, that these devices that we have, these devices, once they will receive the network, the SSID, they will receive the IP information as well, like dynamically getting the IP addresses, dynamically getting the DNS information, dynamic getting the gateway addresses. So all network information, they will get dynamically, because it is the AP will work as a DHCP server as well. So it has the DHCP server. Once they will join the network, once they will connect the network, then they will get those informations as well. But point here is this, okay, in access point, you can go and create the SSID from where you will configure the access point. Suppose if you have 100 of access point, then how within the access point you will go and create the SSID related to employee, related to guest, related to internet, related to other work. So those configurations will come from WLC. From WLC, those configuration will push to the APs, because they have just the DHCP services. All the configurations that is coming from the WLC to the AP. So different pieces here we have to understand as a network engineer, how networking is happening within the access point and these these workstations, and how WLC or how AP will register to WLC and get the configuration. So these parts, they are coming under network engineer category. Let's understand these things one by one. So first of all, what is non-overlapping overlapping Wi-Fi channels? You can see I have created the topics here under the wireless principles. So you will see that we have non-overlapping Wi-Fi channels. The bandwidth is 2.4 gigahertz. They have channel 1, 6, and 11. Actually, the channels that they have, I don't have diagram here, but if you draw those channels, you'll find that they will be like this. Non-overlapping means they are very close, and they are sometimes, if they are overlapping, so a small overlap, sometimes there may be gap in between them, the channels. So gap in between them means if any laptop will go here, he will not get any signal, or the workstations, if the workstation, suppose this star is workstation, so workstation is here and channel is here, so that means he will not get the signal. If workstation is here, his signal is weak. If he is here, his signal is very strong. There may be chances that there is void in the channel. So suppose I have channel 1 and 6, in between them we don't have any interference, we don't have overlapping, so at that time signal strength will be weak or signal strength will be not good. But non-overlapping channel means your channel is like this 1, 6, 11. They are not overlapping. Okay, and then you can see 2.4 gigahertz. These are the spectrum 1, 6, 11 are non-overlapping reducing interfaces. Then we have the 5 gigahertz band. So 2.4 gigahertz band you have, and you have 5 gigahertz band. Then SSID. What does it mean by SSID? SSID is nothing but a network name. Name assigned to the Wi-Fi network can be broadcast visible to clients or hidden. So if I go to my antenna in my laptop, if I go to my wireless network, if I click here to the network, you will see that I'm connected with Ratnesh 314. Then you can see, I can see different network. Chetan, Ratnesh 314 underscore 5. Different network I can see here. I can go and click to a network, just wanted to connect, but it is asking about some security key, some WPA key, some web key, etc. So different channels are there. They are broadcasting the SSID. You need to join the SSID. Once you join the SSID, then you will get the network informations, right? Then radio frequency, 2.4 gigahertz, you have band and you have 5 gig band. Then encryption. So that's the thing I was talking about, that once you try to connect to any SSID, as per the key configured, like it's a WPA2 or it's a WEP. WEP is easy encryption. We'll see that what is WPA, what is WEP in upcoming slide. But this is insecure. WPA 2 and 3, they are good security. WPA 2 is a standard for Wi-Fi security, uses AES, Advanced Encryption Standard. WPA 3 is the latest, offers some more advanced features. These are the topics you have. These are the principles you have, that you need network, you need frequency or the RF frequency to broadcast or receive the network, and then you have the encryption key, security parameters that you will get while joining the network. So what is non-overlapping channel? Non-overlapping channel means you have different bandwidth of channels. So you have the same bandwidth, but they have 6 different spectrum. You can see these are the channels. So different channels, they are non-overlapping channels. In these channels, client can receive some network, or client can go and join the network. Then you have 5 gigahertz band. You can see 5 gigahertz band. So either we are using 2.4 gigaband or we are using 5 gigabit band. Then what is SSID? SSID is nothing but the network we have. SSID is the name of the assigned Wi-Fi network. It used to identify the differentiate and one wireless network from another. Different SSID means different network. SSID equal to network, that you will understand. Then SSID will be broadcasted. So from the AP, they will offer different type of SSID that client can go and join. And while joining, they need some security key. Then we have discussed about the frequency as well. You have different bands and frequencies. Then what about the encryption? Yes, so encryption, you have web key. Now no one is using this because this is very much older encryption and insecure. Wired equivalent privacy, web key. Then you have WPA, that is offering some high level security, Wi-Fi protected access. Nowadays WPA2 is the standard because this is using AES, advanced encryption standard, and this is this AES will be used in IPsec VPNs and other places as well. This is actually very much you can see that there is one story behind this AES, advanced encryption standard. So what happened 15 or 16 years back, or maybe 20 years back, there was one competition in between all the cryptographic algorithms. In that competition, different companies and different programmers, they participated in that competition, and in that they have presented more than hundreds of encryption standard. In that top 5 encryption standard was one was the Batfish, one was AES, and 3 more. I'm unable to recall those. So suppose they are actually very close to win the competition. Advanced encryption, then, and all those 5 encryptions are still in use. They are the best 5 encryption we have at the moment. So after that competition, AES got the maximum marks because it was almost, although it's a encryption method, encryption means that you need some key to decrypt it, but it's something that is almost like impossible to decrypt the AES standard because they are using such type of algorithms, and the keys and the rotation of keys and all those things are there in this AES. And this AES having 3 flavor, they have bit size. The maximum encryption size is 150, 256, 192, and 128. So higher bit means higher encryption, but if you are using higher encryption, if you are using higher hashing and encryption and other methods to protect your network, then you need high CPU resources. So if you are putting more security, then you have to put more processing, and your overall performance of network will decrease. Because what will happen, time to time, different devices, security devices, they have to inspect same type of packets in different manner. So when we are putting all those security parameters, we are checking the requirement of security as well. Security is like, almost depending upon the requirement. Someone is telling like this that you will not put $100 lock in $10 door, right? So it's like that. Security is something that is costly, and while we are choosing the security, so I have to go and choose WPA, WPA2, WPA3. So I will see my requirement that will I go to this or even this. So security is always depending upon the condition. We have all sort of security mechanism and methodologies that is there. And according to that, we are choosing the security parameters. Right, so summary here is this, that we have the non-overlapping channels, we have the SSID, we have the RFs, we have the encryptions, and they are in sync. They are in sync. They are in sync, and according to that, we are working on the parameters, right? Any question, any doubt on this? Please feel free to ask.
I have one. Is there tools that can help you to check if you have interference on the access point, on the
Yeah,
channel that you are transmitting?
so many tools are there. One tool is Ikahau. Other tools are there, yeah. Even if you go and integrate with your DNA, so DNA will present you the picture of this AP mapping. Heat maps are there. They will generate the heat map, and you can, from the heat map, you will come to know that how much interference is there, and according to that, you can segregate the APs, so they will not interfere different channels across each other. So our design should be like this, that the interference should be less. Design means that AP placement.
Okay.
So DNA can do that. DNA, we have that assurance engine in DNA. So once you are discovering the APs in DNA, actually you have to discover the WLC in DNA. Once you discover WLC in DNA, then it will automatically discover all the APs. And then you can go to that design section and you can see that the heat map related to APs, and then you can place that APs properly.
Yes, I saw that in DNA that we have that information, but like thinking more of a more smaller company that doesn't have DNA
Yeah,
there.
tools. Yeah, there are so many tools. Ikahow is one of the
Okay.
tool. Even the customers, the company, they don't want to purchase those tools and licenses. So then they are doing some third-party surveying as well. So you can hire some company with some contract, with some money. They will come with their tools and appliances, and they will do all the survey, and then they will give you the feedback. So multiple options are there.
Nice. Ika House is good tool to have.
Yes,
They
yeah,
help a lot. Okay.
yes, yeah, it's a good tool, and 90% of companies they are using Ikahow.
What's the name again?
I will
How?
Ikahow, yeah, Ikahow. Yeah. I'll put here in the chat.
Yeah, put in the chat because and see that, but I and see that is good. The other company did a site tool for us and they use it.
I mean, again, there are so many companies there. They are doing all this survey and all those things. Tools are there. Ikahow, yeah, Wi-Fi optimization tool. I just put the name in the chat window. You can have a look on that. Let's move on and let's understand virtualization techniques that we have. Now, this topic is very interesting because only VRF is something that we are using within the networking. The server virtualization is nothing but VMware. Container is nothing but Kubernetes and other Dockers type of information. Only VRF you have that is related to networking, right? But let's understand all those things. I have created nice slides here. Server virtualization, what you can do, you can go and install hypervisor within the server, hypervisors like ESXi, Microsoft, KVM, and over these hypervisors, you can go and install different type of operating systems. That is the server virtualization. Container virtualization means you have only one operating system. Any operating system you have. On top of operating system, you can go and install Docker or containers. And on top of containers, you can go and install different packages, different instances of different applications. To manage different Dockers, you have the Docker and Kubernetes type of orchestrations. And then VRF. VRF, again, you'll understand more about the VRF, is virtual routing and forwarding instances. When we are working on Cisco routers or switches, you can go and create, you can go and run any protocol like OSPF, BGP, EIGRP, etc. But with default configuration, they are forming the default or the global routing table. Now, if you want to slash down, so different routers having different interfaces, right? So you can go to different interfaces and you can put different interfaces within different VRF. So suppose this is part of different VRF, this is part of different VRF, this is part of different VRF, and those different interfaces, you can go and create different instances of routing table, right? So that is like one global routing table. You can go and have can create multiple routing tables with help of virtual VRFs, virtual routing forwarding technology. That is very much like virtualization in routing, virtualization in routing techniques, routing tables, right? If you have any question, please feel free to ask. Here, in servers, if you do, that will become server virtualization. In applications, if you do, that will become container. In routers routing table you will do, that will become your VRF. And if you go and use this technology in data center, in data center like ACI or NSXT, that will become tenant. So tenants are what? Nothing but VRFs. Different tenants in ACI, we are assigning with different VRF. So logically they are content. Logically they are separated as a different customers. They behave as a different customer. That is nothing virtualization. And this is a technology that is used practically as well. If you see the concept, related to shopping malls, what is there in shopping mall? They have big giant infra where you have all different products, right? Earlier, how it is, like, different shops are there for different purpose, like medicine shop, then you have some healthcare shop, then you have vegetable shop. What is there in the mall? In one place, you have all those things. Likewise, virtualization means they have the big framework. In that, you have different services. What is the benefit of doing this? What's the benefit you have? Resource utilization, right? Better utilization of resource. That's the benefit, right?
Yes, I guess one.
And then long-term benefit, what long-term benefit you have? If you go and draw the network architecture, you will find this, that you may have different towers. So I have different towers. Different towers means network tower, server tower, application tower, database tower, and other operational towers. Suppose I have a company which has different areas, different towers. Now what you can do with these integration, that you can go and create single automation framework that can go and talk to different towers. What I'm telling, that network, and then server, and then a storage, and then applications, and even cloud as well. Cloud, different towers you have, but you have only one development, or you have only one place from where you can go and manage everything. That is your automation tower. You can do the automation for network, you can do automation for server, you can do automation for storage, you can do automation for application, you can do automation for cloud. Most of the things, most of these repeated tasks can be solved with the infra as a code, IAC, Ansible, Terraform, and even little bit of Python, Ceph, Puppet. These tools, so Ceph and Puppet may be doing some server related and storage related automation. Ansible, Terraform can do cloud related automations. Python, Ansible can do network related automations. So from same platform, you can go and solve these purposes of managing the infra. right? And if you add all these in one bucket, that will become infra as a code. But again, the point here is that how we can utilizing the resources. Utilize the resources, club everything into one place, and then try to manage everything with automation. That will be the goal for all the networking companies, and most of the companies, they have done, some companies have done 60% automation, some has done 80%, some has done maybe 100% is not possible because services are changing and services are too complex. Not only you have even in network itself you have different type of devices. So storage, you have different type of operating systems. In applications, you have different type of dependencies of applications to manage and all. So complexity is there, but if someone has bigger vision, like how we can move all those services in coming 2 years or 3 years or 4 years, then it will become easy to manage the things. But yeah, challenge is there. It's not easy that I'm telling, okay, one platform and manage everything. It is not easy like that. But yeah, it can be doable. All right, so here you can see the diagrams, server virtualization, easy. You have physical server, you have hypervisor, and then you have VMs. Then container, you have one operating system. Over that, you have the Dockers, and then you have the containers. Containers are nothing but different type of packages in one thing. Like packages and libraries and dependencies, you are putting in one box, and that will work as a container. So suppose application A, Python 2, and some DB in one package, and that is associated, that is managed via the Docker. So Docker can go and manage n number of containers, right? So here you can see that load will be less. You have to manage only one operating system, but you can manage n number of applications. VRF is what? You are slicing the global routing table into multiple routing table for different customers. So customer A is associated with VRF A, customer B is associated with VRF B. Like that we have. Server virtualization, containers, as we discussed, and this you will understand more in our automation section. In CCNA DevNet, you will understand about CI/CD pipelines, the application development theory, the architecture, microservices architecture, theory principles. Those things are covered more in the DevNet course. Server virtualization is something related to VMware. VRF, I will explain you more about this in the BGP section, because if you are slicing the global routing table, then you have to go and use it as well, right? And if you are connected with multiple ISPs, then you can go and use that VRF technology within the BGP, that we will see later on. Then what I have done, I have this comparison chart here just for your reference, that server virtualization, container, and VRF, what they are doing, what's the use case, just for your reference. In terms of overhead, I just wanted to highlight this. Overhead, the VRF is, you can't compare all these three actually, because this is different thing. You can compare server virtualization and container in terms of application. So in terms of application, you will see that overhead is low because you have to manage only one operating system. The server virtualization overhead is more because you have multiple OS to manage, right? And in terms of speed also, this is very fast because they are very close to the applications. So that's why you will see the rise of Kubernetes and containers. Everyone is talking about Kubernetes containers because they will enhance the application performance and reduce the cost drastically. Right. And then again, some of the differences and the similarities you have. So far, if you have any question, query, please feel free to ask.
No, I'm good.
Okay, great. So now we have last topic. It's very easy topic. It will take hardly 5 to 10 minutes to understand. that describe the switching concepts. Switching, how switches are working. Switches, they are very nice, gentle devices that if you go and connect anything with the switch, and they are working at the layer 2. So if you connect anything to their interfaces, let me try to draw some interfaces. I suppose port 1, port 2, port 3, port 4, port 5, up to port 48, up to port number 48, right? So if you go and connect anything to these switches, they are very nice devices. They will learn you. Yeah, you're telling me something. Okay, let me mute you. Okay, so they are very nice, gentle devices. If you connect anything to them, they will go and learn your IP address. Not IP address, MAC addresses, because they are working as layer 2 in the data link layer. Data link layer deals with MAC addresses, but point here is this: they will learn your MAC address if you send some frames to this interface or via this interface. Suppose you are connected, and if you are idle for 300 seconds, then they will flush your MAC address as well. So these switches, they are building the MAC table. MAC table is nothing but the port plus the MAC address. Port like gigabit Ethernet 00, and then the MAC address A, B, 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 C, 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 D, D, D. Right? So they have something called CAM table where they are building where they are learning the MAC addresses, and they are building the MAC table. That's the last topic you can see here is the MAC address table. So switches, they are learning the addresses and they are building their tables. That is nothing but the MAC address table, but they are learning and they have the aging time of 300 seconds. That means 5 minutes. So if you do not send receive traffic within the 5 minutes, they will flush the MAC entry from their CAM table. Why? Why they are doing this? Because they don't want to unnecessarily populate their database. They will not learn something that they are not using for a long, because they have limit that how many MAC addresses they can learn. So if you go and check the blueprint, you will see that lower end switches can learn up to 30,000 of MAC addresses. Higher end switches can learn up to 64K MAC addresses. Like that, they have the limit 128K thousands, 128,000 MAC addresses. So they have the limits that how much MAC addresses they can learn and store. So that's why they don't want to learn unnecessary things that they are not using. Unnecessarily, we should not populate their cache, their memory. So that's the MAC learning. Then you can see that we have the frame switching and frame flooding. Frame switching means switches, they are dealing with frame. Layer 2 packets are termed as a frame. Layer 3 packets are termed as a packet, right? So when you have payload and MAC address, that is nothing but frame. So if I go and build packet here, and packet and frame, by the way, they are two different terms. So suppose this is your packet. Let me try to draw here. Let me write here. So suppose this is something that you have some payload, and then suppose you have source MAC, and then suppose if we have destination MAC, source MAC and destination MAC. So if you have such type of packet, this will term as a frame. But if I go and draw like this, and two more. If I go and draw a diagram like this, that you have payload, and then you have source MAC, you have destination MAC, you have source IP, you have destination IP, then this will be packet. And if you go and add the port numbers, then they will start building the session. So frame where you have payload and the MAC addresses. So what is frame switching? Frame switching means that this will go to the switch interface. Suppose you have the switch and switch having interface. So you will send the packets, not packets, you will send the frame, right? You will send the frame where? To this. Now this interface, suppose this is the source of the frame, but your destination is connected here. So what switch will do? Switch will shift the frame from one interface to other interface, because then they have to go to the other interface where they have the destination. So that is nothing but the frame switching, concept of the frame switching. Somehow switch knows that this port having this port, that's the, with the MAC table, they will come to know that this is the port and this is the MAC address that's related to source. But I have to send this particular MAC to this particular MAC, that is source MAC to the destination MAC. How? Because when the switch will receive the frame, you can see when they are receiving the frame, they will go and open that frame. They will read, oh, this is the source, this is the MAC I am getting, this is the source address, but where I have to switch this frame. So there they have this destination frame, right? Oh, this is the MAC address. Again, what they will do, they will check their CAM table. They will go and check their MAC table. In their table, they will see, oh, this is the table. I can see that the source I'm getting is over the port number gig00. The source MAC I'm receiving is over port gig00, but the destination is over gig0/10. The destination MAC that I have to send is over gig0/10. So what switch will do? Simply it will send the 00 packet to 010 packet, right? Not packet, but frame. So 00 frame to 010 interface, because they have that frame should reach to the destination, because the destination you have the obviously you have the destination host. So here you have the destination. Suppose this is the source PC, and suppose this is the destination PC. Source PC and destination PC. So source PC and destination PC. Source MAC address receiving on this switch will do frame switching. So it will go to this interface, and from this interface it will go to the destination. So source can get to the destination, but there is one catch. Then suppose if the switch is not knowing where to send the destination frame, if switch doesn't know, what the switch will do? In that case, they will do frame flooding. That means the source will be any known MAC address, but the destination will be all FFF, broadcast address, FFF, broadcast address. That means that they will go and send that packet to all the interfaces except the interface that they are receiving the frame. So that means that if this switch having different 47 or 47 different ports, then they will broadcast this particular frame to all those interfaces with this MAC address, because they don't know what is the destination MAC, and that is termed as a frame flooding. So let me show you the slides we have. MAC learning. Let me go here. MAC learning switch will learn the MAC addresses as an incoming frame. When they will hit the interface, they will go and learn it, but there is aging time. The aging time is 300 seconds that you can increase or decrease. Then frame switching is this, that they will receive some frame and send the frame to the destination. The source frame should be forwarded to the destination frame where you have destination PC. That's the frame switching. Frame flooding is something that they do not have the destination. So if switch receive a frame with a destination MAC address is not in its MAC table, then it flood the frame out to all the port except where they are receiving it, right? This ensures that the frame reaches the destination even if the switch does not know the exact destination. That's the flooding, flood everywhere. Then MAC table, we know that.
Question there, Ganesh. Uh, what will be an actual case of a frame floating, right?
The VMware workstations,
Okay, so the virtual machines.
yeah, virtual machines, and suppose that that is one use case, but apart from that, other use cases are also there. Let me explain here. So suppose this is one switch, and these are the PCs, and these are the PCs. Now assume that when they start communicating, then only switch will learn the MAC address, right? Suppose they are not communicating, and then you have to send a packet or frame more precisely. So you are sending the frame, but switch has flushed these entries. Switch don't have these entries.
Okay, yeah.
So then in that case, they will flood, because in their CAM table, they don't know the destination. But in the actual packet, the destination is there. But switch CAM table don't know the destination. So they will send that packet to all the interfaces, and whoever PC will receive that MAC address. So he will come to know, oh, this is my address. That means I should respond. At the moment they will start responding, switch will again learn the MAC table, MAC address, right?
Yeah. Okay.
This is very much, a legacy way that switches, they are building the MAC table. This is not the way that we are building the MAC table in data centers. Building the MAC table in data centers nowadays is more proactive, and they are using some different type of method to do that in data centers.
Ganesh, and how about if after the frame flooding,
Flooding,
the
yeah,
MAC,
frame flood.
the destination MAC address is not found? What
Then it will
happens?
drop that. Then packet drops will happen. Destination unreachable things will come. Because that is not exist in that particular switch, then obviously that particular switch will flood that to the upper layer switch, and then the upper layer switch, and then you can see frame flooding everywhere. This may cause high CPU, CPU spike in the switches, and this may be one type of DOS attack as well. It's not only that this switch will flood the frame, flood the packet. So what will happen? So suppose this switch is connected with 10 different switches, and again they have the chain of switches that is connected. Now, since they do not know the destination, this will flood to these switches, and these switches will flood to the uplink switches, and the flooding of broadcast packet, it will be there in the entire switching infra. Okay, this is a good question. So we should protect from this flooding attacks as well, and that's why we are limiting the bandwidth for the floods and the unknown broadcast, bum traffic, BUM, broadcast, unknown unicast, multicast. You should limit that. Oh, all right. So then they are building the CAM table, and CAM table, they make sure that things are in the right set. Oh, we completed our day. Wow. So far what we have done, we'll check the syllabus in next session, but we have completed actually section 1 of our CCNA. Let me open that syllabus. Let me pause the recording and open the syllabus. I'll show that where we are at the moment, how much coverage we have done. Let me pause the recording.